The furnace at the steel shop is loaded with selected iron scrap, melted by an electric arc created between the electrode and the scrap. Around 100 tons of metal is loaded in the furnace in 2 different steps. Chemical energy is provided by various oxy-fuel burners, supersonic oxygen lances, and carbon injectors, all located in the furnace walls. When all the scrap has been melted and tapping conditions are reached, around 95 tons of liquid steel at around 1,650 degrees Celsius are poured into the ladle. Liquid steel is refined in the furnace by argon bubbling. Ferroalloys are added to achieve the ideal chemical composition. Temperature is carefully controlled to allow the best casting conditions. At this stage, vacuum degassing for special steels is performed. Continuous casting turns liquid steel into round solid bars with diameters of between 148 and 395 millimeters for rolling. Throughout the whole process, operators continue to take samples of steel and slag, adjust chemical composition, and control temperature to ensure consistent quality. An integrated system controls production, including the melting profiles in the furnace, emissions, ferroalloy additions, and casting parameters until the bars are cut to length. The bars are cut to length to produce billets of precise weight for the final tube dimensions. These billets are loaded into a natural gas-powered rotary heart furnace for heating. Billet sizes relate to the final tube dimension, while heating time is related to the billet size. The final billet temperature is around 1,250 to 1,300 degrees Celsius. The billets are then transferred to the hot rolling mill for piercing. The rotary piercing process transforms the hot billet into a hollow shell. During this process, the material advances on a helicoidal pattern driven by 2 rollers. The rolls generate internal tension and a cavity forms in the billet. The piercing plug then enters this cavity. The resulting hollow shell is a rough, short tube with a large diameter and thick wall. Now elongation must occur to turn the shell into a finished hollow tube. Elongation is performed in the mandrel mill by reducing the wall of the hollow shell between 6 to 8 sets of double rollers and a mandrel previously inserted into the hollow shell. During this process, the outside diameter and wall of the hollow shell are reduced, elongating the shell and transforming it into a mother pipe. The mother pipe is then sent to the last stage of the rolling line, the sizing mill, to set the diameter and wall thickness of the tube according to customer needs. The mother pipe is sized, reducing the outside diameter between 3 to 7 sets of double rollers. Tenaris guarantees a very high level of automatic control of the rolling process based on measurement of the field variables and mathematical models to guide the operators. During the rolling, tube parameters are measured by laser imaging and X-ray techniques to check the rolling results in real time. Mother pipes with an external diameter of 360 and 406 millimeters are used to form large diameter pipes. After heating, mother pipes are expanded through a cross-rolling mill on a taper plug. The reduction in thickness is compensated by the increase in the tube diameter. The expander mill can produce tubes with an external diameter of 406 to 711 millimeters. The mill is highly automated and allows the furnace to reach homogeneous temperature. Mathematical models are used to check and define the setup of the rolling mills. Laser techniques are used to check the rolling results in real time. Tenaris guarantees tube quality with non-destructive techniques, ultrasonic, flux leakage, and magnetic particle tests depending on the type and size of tubes. Tubes are cut, spectrography is used to check tube chemical composition and avoid steel mixing. Finally, tubes are marked by punching or stenciling, then surface is protected and packaged according to customer needs. Thanks to the latest technology and process automation, Tenaris guarantees a high reliability of its final products.